Next chapter, air and combustion. Now, as you may already know, we live in an ocean of air, the atmosphere. This largely transparent part of our environment reveals itself when it starts to move, shaking the trees and blowing away materials. Air, of course, plays an important role in life. The chemistry of air is fully integrated into the chemistry of life. Oxygen and carbon dioxide flow between plants and animals, packaging and releasing energy from the sun. As we said before, air is a mixture of various gases, water vapor, and dust particles. The approximate composition of air is about 78.08% nitrogen, 20.95% oxygen, 0.93% argon, 0.04% carbon dioxide, and between 0 to 4% water vapor. The amount of these gases may vary from place to place depending on seasons, altitude, and human activities. For instance, the amount of carbon dioxide and dust is higher in cities and industrial areas than in forested places. Combustion. Humans do a lot of burning. We burn wood. We burn fossil fuels, coal, petrol, and natural gas. And sometimes we burn hydrogen. In all these burnings, the substances that burn combine with oxygen to release energy, usually heat and light. Reactions of this type are called combustion reactions. But energy is not the only product of combustion reactions. For example, when we burn coal, we produce carbon dioxide as well as energy. And when we burn hydrogen, we get water as well as energy. In both of these, the chemical products are gases that are released into the atmosphere. Some combustion reactions are very fast. If you mix hydrogen and oxygen gases before setting them alight, the reaction occurs in a split second. We call it an explosion rather than burning, and it's the same inside the car engine. The fuel is mixed with air in the cylinder and explodes with a spark from the plug. But put the same gas in a cooking stove and it burns. It is the same combustion reaction, just happening at different rates. Combustion reactions are very important to humankind. We use them to keep warm, to heat water, to cook, to move cars, ships, and planes, for manufacturing, and to produce electricity. In this chapter, we shall focus on the oxygen part of the air. When we say that oxygen constitutes about 21% of the air, it is not a theory. We can be able to experimentally determine this percentage. Oxygen is the only part of air that supports combustion. When a candle is lit and left exposed, it continues to burn due to adequate supply of oxygen from the surrounding air. But if the candle is covered with a glass, it goes off after a brief moment, and that's because the oxygen within the glass is depleted. Let us perform an experiment to determine the proportion of air that is used up when copper is heated in a fixed volume of air. Now, when brown solid copper is heated, it combines with oxygen to form a black copper 2 oxide. It is this oxygen that combines with the copper that we will measure using syringes. We set up the experiment like this. We light the Bunsen burner and heat the tube with the copper powder inside. We then start moving the syringe to and fro about 50 times to pass air over the heated copper. We continue the heating and moving. All the air has to move over the hot copper so that the oxygen in the air can combine with copper to form copper 2 oxide. At some point, there would be no further change in the amount of air in the syringe. At this point, there will be some brown copper that has not reacted because the oxygen is depleted. We collect our data and do the calculations. The original volume of air was 100 cubic centimeters. The final volume is 80 cubic centimeters. So the volume of air that has been used is 100 minus 80, which is 20 cubic centimeters. We calculate this percentage. 20 over 100 times 100 gives us 20%, which is a good approximation. When substances burn or react with oxygen, we call it oxidation. So copper metal is oxidized to copper 2 oxide. Combustion reactions are also oxidation reactions. Oxidation, or the addition of oxygen to a substance, does not necessarily have to occur when heating is involved. For example, over a period of time, oxygen will combine with iron, producing rust. The ugly reddish-brown color on this roof is rust. It is a form of iron oxide. It is an oxidation process that occurs slowly without any heating involved. We can also use the chemistry of rust to establish the percentage of oxygen in air. We need some steel wool, which contains iron, also a plastic test tube, and a container of water. The process is simple. We place a damp iron wool at the bottom of the test tube. We overturn the test tube into the water container. The oxygen in the tube will react with the iron wool, forming iron oxide, rust. This removes the oxygen from the air in the tube. The volume of the used up oxygen is taken up by water, which rises in the tube. When the process is finished, the added volume of water in the tube equals to the volume of the removed oxygen. Let's set up the experiment now. These plastic tubes are calibrated in milliliters. We made a hole at the 10 milliliter mark. This is the starting volume of air. Water will enter the tube up to this point. A hole in the cap allows water through the base. To increase the rate of oxidation, we dampen the iron wool with dilute acetic acid, common vinegar. Push the iron wool to the bottom of the tube. Invert the tube into the water container. We can set up a control with a tube that has no iron wool in it. So the two tubes are now in place with the initial volume of air at the 10 milliliter mark. The process is very slow. This time lapse covers 1 hour. In this time, the water moves 15 milliliters on the scale. As the oxygen depletes, the process slows down even more. If we let the setup stand overnight for about 8 hours, the next morning, the water has settled at the 8 milliliter mark. The water level in the control is unchanged. From the original volume at the 10 milliliter mark, 2 milliliters have been replaced by water. This volume represents the amount of oxygen removed from air. So in our calculations, initial volume is 10 milliliters. The final volume is 8 milliliters. And the volume used is 2 milliliters. As a percentage, 2 over 10 times 100 is 20%. Again, a good estimation. And now, Separation of the components of air. Nitrogen, argon, and oxygen can be separated from the air by liquefaction followed by fractional distillation. First, the air is filtered to remove dust. It is then cooled in stages to negative 200 degrees Celsius, at which temperature air is a liquid. As it is cooled, water vapor condenses and it's removed by absorbent filters. Carbon 4 oxide is then removed at negative 79 degrees Celsius when it freezes. Alternatively, it can be removed by passing the air through sodium hydroxide solution. This leaves oxygen, nitrogen, and argon. The oxygen liquefies at negative 183 degrees Celsius, argon at negative 186 degrees Celsius, and nitrogen liquefies at negative 196 degrees Celsius. The liquid nitrogen, argon, and oxygen are then separated by fractional distillation. This liquid mixture is passed into a fractionating column. It is then gently warmed. When the temperature gets to negative 196 degrees Celsius, nitrogen boils out and it's collected. When it reaches negative 186 degrees Celsius, the argon boils off. And when it reaches negative 183 degrees Celsius, the oxygen boils out. The important uses of nitrogen are creating an inert atmosphere for chemical processes, the Haber process for the manufacture of ammonia, gas chromatography, packing oxidizable foods such as ground coffee, and also liquefied nitrogen can be used for the freeze drying of foods and preservation of tissue samples. Argon helps to create an inert atmosphere around filaments in light bulbs. Much more spectacularly, blue argon lasers are used in surgery to correct eye problems, and scuba divers use argon to inflate dry suits. Finally, oxygen is essential for our breathing and survival, and is therefore used in medicine for breathing equipment. Oxygen is also used for steel making. It is passed through impure iron in a blast furnace to oxidize and remove impurities such as carbon, sulfur, phosphorus, and silicon. It is also an important part of rocket fuel, and it's used to fuel oxyacetylene flame for cutting and welding. Next, we look at rusting. Now, you definitely must have noticed that new shiny iron nails will over time turn brownish when exposed to air. This brown substance is called rust. When iron and steel are exposed to oxygen and moisture, rusting will occur. Rusting describes the corrosion of iron and steel. The term corrosion is used to describe the breakdown of metal when exposed to the environment. When we say a metal corrodes, we mean that it has reacted with water and oxygen from the environment to form their respective oxides. We can demonstrate the conditions for rusting using a simple experiment. Place iron nails in 4 test tubes. Fill one with regular tap water until the nail is submerged. Fill another with regular tap water and add half a spoonful of sodium chloride or the common table salt. Mix them well. Fill the third one with boiled water and add a thin layer of oil. Boiling removes dissolved oxygen from water. Oil prevents any entry of oxygen from the air. To the 4th test tube, add a spoonful of calcium chloride. Calcium chloride removes moisture or water. Put stopcocks at the mouth of all the test tubes and leave them for some few days. You will find that the nails in the 1st and the 2nd test tubes have rusted, with more rusting in the 2nd test tube. In fact, the rust may have slightly flaked off. you may see a reddish-brown precipitate at the bottom of this test tube. The nails in the third and fourth test tubes have not rusted. In the third test tube, the nail is exposed to moisture but no oxygen, so no rusting. In the fourth one, the nail is exposed to air but no moisture, again no rusting. And so we confirm that oxygen and water are the two necessary conditions for rusting. Salty and acidic environments as well as high temperatures only accelerate the process of rusting. This is why vehicles in the coast region rust faster than those in the inland areas, because the coastal environment is salty. So chemically, rust is hydrated iron 3 oxide. It occurs due to reaction of iron and oxygen in the presence of moisture. Prevention of rusting. Now, rusting can be very costly if we have to constantly replace these items made of iron and steel. When you think of cars, you might know that they are painted. The paint is not only there to make the car attractive, but it has a more important purpose of preventing rusting. Rusting can be prevented by painting the areas exposed to oxygen and moisture. Another method is by applying a layer of oil or grease. When placed on, say, a bicycle chain, it helps to lubricate the moving parts, which reduces friction as well as prevent contact with air and moisture. Another way is a sacrificial method called galvanization. For instance, zinc is more reactive than iron. When exposed to oxygen and moisture, zinc will corrode faster than iron. So if we put them together, zinc protects iron by sacrificing itself, hence the term sacrificial protection. So galvanization is a sacrificial protection method where things made of iron are coated with zinc, and the zinc reacts with oxygen, leaving the iron safe. Next, we look at oxygen. Oxygen can exist freely or combined into compounds. It exists freely in the atmosphere as a colorless gas. Here, two atoms of oxygen combine to form an oxygen molecule. Oxygen can also be found combined with other substances. Like in water, it is combined with hydrogen. And in carbon dioxide, it is combined with carbon. Oxygen is prepared in the laboratory by decomposition of hydrogen peroxide. Hydrogen peroxide is a colorless, heavy and strongly oxidizing liquid with a chemical formula H2O2. It is highly unstable and slowly decomposes into oxygen and water. The process can be fastened by using manganese oxide, which acts as a catalyst. We set up the apparatus as shown here. Some manganese oxide and water are taken in a conical flask. Hydrogen peroxide is added dropwise through the thistle funnel. Oxygen gas is liberated and carried through the delivery tube. It is collected in the gas jar by downward displacement of water. This is possible because oxygen is only slightly soluble in water. We said the manganese oxide is used as a catalyst. A catalyst is a substance that alters the rate of a reaction process, but without itself being changed. Other methods of preparing oxygen include adding water to sodium peroxide, heating potassium manganate 7, and heating potassium chlorate. Physically, oxygen is a colorless and odorless gas. It is less dense than air and it's slightly soluble in water. It is a gas at room temperature and liquefies at negative 183 degrees Celsius. Chemical properties. Burning substances. We start with metals. Metals burn in air at different rates. Magnesium burns in air with a bright white flame to form magnesium oxide. Calcium burns with a brick red glow to form calcium oxide. Sodium burns with a yellow-orange flame to form sodium oxide. Potassium burns in air with a lilac flame to form potassium oxide. And so in general, metals burn in air and combine with oxygen to form metal oxides. This addition of oxygen to a substance is called oxidation. The metal oxide has more mass than the metal due to addition of oxygen. Reactions with nonmetals. Nonmetals also burn in oxygen to form oxides. The oxides of nonmetals are acidic in nature. For instance, if we burn phosphorus in a china dish with a glowing splint, it produces white fumes of phosphorus 5 and phosphorus 3 oxides. Let's cover these fumes with a gas jar. We invert the gas jar upright and add some water. The white fumes dissolve in water. Now we add a few drops of blue litmus solution. The blue color changes to red, indicating it is acidic in nature. Carbon, like coal, burns with a yellow flame to form carbon 4 oxide. Sulfur burns with a blue flame to form sulfur 4 oxide. Next is competition for combined oxygen. Now, elements differ from one another in terms of their appearance, properties, uses, and reactivity. Gold, for example, is yellow, relatively hard, and very unreactive. Potassium, on the other hand, is gray, relatively soft, and reacts vigorously with oxygen and water. We can actually organize these elements according to their reactivity. This arrangement is called the reactivity series. The most reactive elements are at the top and the least reactive at the bottom. A more reactive element will displace the lesser reactive element from a compound. For instance, if A is more reactive than B, then A will displace B from the compound BC to form the products AC and B. This is called a displacement reaction. So we use the reactivity series to predict if an element will displace another from its compound. The thing is, an element will only displace another if the first element is more reactive. This applies even to oxides. Consider copper and carbon. Carbon is more reactive than copper, so carbon will displace copper from its compound, like copper 2 oxide. Copper 2 oxide is a black powder. We place 3 spoonfuls of copper 2 oxide in a crucible and 1 spoonful of charcoal, which is a form of carbon. We heat the mixture for approximately 5 minutes. We remove the crucible from the flame and empty the content into a beaker of cold water. We pour out the water and the charcoal. We rinse again. You will find a red-brown solid at the bottom of the beaker. This is copper. What has happened is that carbon has displaced copper in copper-2 oxide to give copper metal and carbon-4 oxide. This process is used in the extraction of copper from its ore, called malachite, which is copper-2 carbonate. The copper-2 carbonate is first decomposed by heat to form copper-2 oxide and carbon-4 oxide. Then through displacement reactions, we extract the copper metal from the copper-2 oxide using carbon. Next, test for oxygen and carbon-4 oxide. Now, we test for gases in the laboratory because it is impossible to identify a gas just by its appearance. To test for oxygen, place a glowing splint at the mouth of the reaction vessel. It's a glowing splint, not burning. A glowing splint relights in the presence of oxygen. The splint relights because there is a higher concentration of oxygen in the vessel than in the atmosphere, which is only about 21%. Carbon-4 oxide will extinguish a burning splint, but the same will occur with ammonia. A more accurate test is to bubble carbon-4 oxide through lime water, which is an aqueous solution of calcium hydroxide, also called slaked lime. A white precipitate is formed. Carbon-4 oxide reacts with soluble calcium hydroxide to form an insoluble calcium carbonate, which is the white precipitate. Finally, air pollution. Now, whereas combustion reactions have made life a lot easier, they are not always helpful and can get out of hand. If you live in a city, you may already be aware of some effects of air pollution on your health. You may already have had breathing difficulties or painful eyes. Common air pollutants include particulate matter, ozone, nitrogen oxides, and sulfur oxide. These pollutants exist as a result of human activities. One such activity is the burning of fossil fuels in industries and in automobiles. Particulate matter is a mixture of sulfates, nitrates, ammonia, sodium chloride, carbon, mineral dust, and water. It consists of a complex mixture of solid and liquid particles of organic and inorganic substances suspended in air. They differ in their sizes. Small particles are the most dangerous because once inhaled, they may reach the lungs and can interfere with gaseous exchange. Chronic or prolonged exposure of solid particles can contribute to the risk of cardiovascular and respiratory diseases, typically asthma as well as lung cancer. Ozone absorbs harmful UV radiations from the sun in the upper atmosphere and can help prevent the increased risk of skin cancer. However, ground-level ozone causes problems. It does so by a chemical reaction which is triggered by absorption of light. The reaction between nitrogen oxide and volatile organic compounds leads to formation of a photochemical smog and ground ozone. This is seen mostly in summer and can appear as an orange-brown hail over the city. This smog in the ground ozone causes breathing problems, can trigger asthma attacks, and lead to lung diseases. Nitrogen-4 oxide emissions come from cars and factories where fuels are combusted. We know that oxygen forms about 21% of our atmosphere, while nitrogen forms around 79%. In a car engine, A tiny amount of nitrogen combines with oxygen to form mixtures of nitrogen oxides. Studies have shown that there is a close relationship between the signs of bronchitis in asthmatic children and the long-term exposure to these pollutants. Sulfur 4 oxide is formed when sulfur-containing compounds are combusted in the presence of oxygen, mainly coming from fossil fuels which contain traces of sulfur, and also smelting of mineral ores leads to formation of sulfur 4 oxide. In turn, these pollutants affect the respiratory system and cause eye irritation. If you inhale them, you are likely to develop a cough, secrete more mucus, and will be at a higher risk of developing chronic bronchitis. In summary, all these are causing unnecessary deaths, especially where the emission of these pollutants can be avoided, like the use of catalytic converters in cars and by scrubbing of power station gases.
It's important to mention that ancient civilizations weren't just big doers, they were also big thinkers. While the Indians were mastering steel, philosophers in ancient Greece, like Democritus and Aristotle, started asking questions of how nature is put together. Many consider Democritus to be the father of modern science. Democritus and his mentor Leucippus developed the idea that everything is made of atoms, an infinite number of indestructible units of all shapes and sizes that have always been, and always will be, in motion. Some modern historians and scientists say Democritus simply got lucky, and recent evidence just happens to confirm his hypothesis. But the Greeks weren't that thrilled with Democritus either. Rumor has it that Plato, another thinker of the time, wanted all of Democritus's works burned. Plato thought Democritus was too materialistic, that ideas ruled the universe. Democritus and Plato, the Hamilton and Jefferson of their day. But like some sparring heads of state, parts of both their ideas contributed to the formation of science. Though, after several centuries, it turns out Democritus was more correct with his atomic theory.